Look up into the night, and it's easy to feel comforted by the sheer abundance of light. Stars scattered like distant embers. A Milky Way so wide, it seems impossible for it to belong to just one small world. When you zoom out in your mind, the numbers become almost soothing in their excess. Hundreds of billions of stars in our galaxy alone. And around them, worlds, rocky planets, icy moons, oceans hidden under crusts of frozen glass. Across the observable universe, billions of galaxies, each with their own seas of suns. With a stage this large, it feels ordinary to assume the play has begun many times, that chemistry has sparked, that biology has climbed, that intelligence has opened its eyes under alien skies. In a universe so big, life can seem less like a miracle and more like an inevitability. And yet, the sky does not answer. We listen, and we hear nothing that can't be explained by wind, by static, by the restless hum of our own technology. We scan the stars for patterns, for beacons, for the telltale warmth of sprawling machines. We imagine that if civilizations were common, if even a small fraction survived long enough, they might leave fingerprints across the galaxy, a stray transmission, a city's waste heat, a probe drifting between stars. But the contrast remains, a universe that should feel alive, and a silence that feels complete. This is the familiar question that refuses to leave us alone. It's called the Fermi Paradox, named after physicist Enrico Fermi, who essentially asked, if the universe is so vast and old, and if life should arise in many places, then where is everybody? Not where are they hiding, or why haven't they visited us specifically, but why do we see no clear sign that anyone has ever crossed the threshold into a lasting, visible, spacefaring presence? At first it sounds like a clever puzzle, but the longer you sit with it, the more it behaves like a shadow, because it doesn't just ask about them, it asks about us, about whether our own future is something the universe commonly allows, or something it quietly erases. And that's where a darker possibility emerges, one that is both scientific and deeply existential. The great filter. The idea that somewhere along the long path from dead matter to a civilization that can spread among the stars, there is a step, or several steps, so brutally difficult that almost no one makes it through. Maybe life rarely begins at all. Maybe complex cells are the true miracle. Or maybe intelligence blooms easily, and then, almost as easily, collapses. The great filter is not a single monster you can point to in the dark. It's a name for the possibility that the universe contains a gate, and most travelers never pass it. Tonight, we're going to trace that path carefully. We'll drift back to the early bottlenecks of evolution, when Earth itself may have balanced on a knife edge between chemistry and life. We'll consider the fragile moment when technology turns from tool to threat, through war, through engineered pathogens, through the quiet escalation of risk. We'll talk about artificial intelligence, not as a movie villain, but as an unprecedented kind of power that might be difficult to align with survival. We'll explore climate collapse, resource exhaustion, and the slow, unglamorous failures that can unravel even a brilliant species. And hovering over everything is the most unsettling question of all. Is the great filter behind us or waiting ahead? Because the answer changes how we should think about progress, caution, and what it means to grow up as a civilization. If you enjoy late-night science, cosmic mysteries, and questions that unfold slowly in the dark, you're warmly invited to like this video. And if you'd like more quiet explorations of space, physics, and the strange future of intelligence, you can subscribe and join us again. For now, just return your attention to the silence above you. Because the first uneasy realization is this: the night sky may not be peaceful. It may be empty for a reason. And every star system we pass in our imagination, every calm, unlit orbit, could be a place where the story ended, long before it could ever be seen. But to understand why the universe may be so silent, we first need to ask where exactly civilizations might be disappearing. The Milky Way is not a young place. It is an ancient spiral of stars that has been turning for a very long time, long before Earth cooled, long before the first oceans settled into their basins, long before the first cells learned the quiet trick of copying themselves. Our species has been here for a flicker. Modern humans, as we'd recognize them, have walked beneath the sky for something like a few 100,000 years. Agriculture is only thousands of years old. Radio, our first unintentional lighthouse into the cosmos, has been leaking out for barely more than a century. and the galaxy has been waiting for billions of years. That difference in scale is what makes the Fermi Paradox feel so disturbing. Not because it's clever, or because it's fun to imagine aliens, but because time is the great amplifier. When you give the universe enough time, even unlikely events start to feel like they should happen somewhere. When you give a civilization enough time, even modest ambitions can turn into something enormous. The oldest stars in the Milky Way formed more than 10 billion years ago. Many planetary systems are billions of years older than our own. That means the galaxy had a long head start, an almost unimaginable runway of time, during which life could have risen, stumbled, recovered, and risen again. Not once, but many times. On worlds that had oceans before Earth even existed. On continents that eroded away before our planet had its first forests. And if even one of those worlds produced a civilization that reached a stable technological phase, not perfect, not all-knowing, just stable enough to keep going, then even a small head start becomes overwhelming. Because 1,000,000 years is an eternity to a species with tools, 10 million years is a blank canvas. 100 million years is enough time for entire lineages to evolve and disappear on Earth, multiple times over. Now imagine a civilization that got started not 10,000 years before us, but 10 million. Imagine they developed industry while Earth was still dominated by early mammals. Imagine they built their first radios while the dinosaurs still ruled here. Even if they were slow, even if they were cautious, even if they were not particularly interested in conquest or colonization in the dramatic human sense of those words. The age of the galaxy suggests they would still have had time to do something, anything, that would make their existence obvious. This is why cosmic age magnifies the mystery. It turns the question from could anyone else be out there into how could no one have left a mark by now. The Milky Way is old enough for many attempts, old enough for countless experiments, old enough for civilizations to rise and fall like waves. And yet, when we look out, we see a kind of stillness, a calm, unlit orbit, a silence that feels too complete for a galaxy that has had so long to try. And here is the next uncomfortable step. The paradox doesn't require a crowded galaxy. It doesn't require millions of civilizations all shouting at once. It doesn't even require that intelligent life be common. It only requires one civilization that survives long enough to become interstellar, one that keeps going, generation after generation, one that builds ships, or probes, or self-replicating machines, and releases them into the dark between stars. Because even slow expansion, on cosmic timescales, is fast. The Milky Way is about 100,000 light-years across. That sounds impossibly large, and in a human lifetime, it is. But if you imagine an interstellar species traveling at even a small fraction of the speed of light, or sending robotic explorers that can drift, hibernate, and endure, the numbers start to become unsettling. A ship traveling at 10% the speed of light could cross the galaxy in about 1,000,000 years, give or take. And 10% is ambitious by our standards, but not beyond the laws of physics. Even 1% of light speed, still staggeringly fast to us, stretches the crossing to 10 million years. Add in pauses, settlement time, failures, detours, and you can slow it down further. But the galaxy has had billions of years. Even if expansion took not 10 million years but 100 million, that is still a small slice of the Milky Way's lifetime. It is the kind of timescale that fits comfortably inside the margin of plenty of time. A civilization doesn't need to race. It doesn't need to fill every star system immediately. It just needs to spread, gradually, like a slow-growing forest. And there is an even more haunting idea. It might not even be biological beings doing the traveling. A civilization could send machines, small probes that mine asteroids, build copies of themselves, and move on, not as a swarm of warlike invaders, but as an automated exploration program. A patient, unfeeling, persistent presence. If such probes are possible, and many scientists think they are at least conceivable, then a single civilization could seed the galaxy with artifacts that multiply as they go. And once you admit that possibility, the expectation changes. You don't need 1,000 alien empires. You don't need a crowded cosmic community. You only need one long-term survivor with curiosity, or caution, or ambition, and the galaxy should look different. It should look used. It should look visited. It should look like someone has been here before. Which brings us to the part that makes the silence feel heavier than a mere lack of conversation. We have listened. For decades, we have aimed antennas at the sky and searched for patterns in radio waves. We have looked for narrowband signals, for repeating pulses, for anything that feels engineered rather than natural. We have scanned regions around nearby stars. We have catalogued strange bursts and odd emissions, and most of them, with time and study, have turned out to be the universe doing what it does best, being complex, being violent, being beautiful, without any need for intention. We have searched for probes, objects that might be hiding in stable orbits, perhaps in our own solar system, perhaps in the quiet gravitational pockets where a machine could watch without being noticed. We have imagined artifacts on the moon, where there is no weather to erase them quickly. We have thought about the asteroid belt, about the Lagrange points, about the places a patient observer might choose. We have also searched for the grander fingerprints, the idea that a very advanced civilization might reshape its environment on stellar scales. The classic example is the Dyson sphere, an enormous structure or swarm built to capture a star's energy. We have looked for stars that seem dimmed in strange ways, or that radiate unusual infrared heat, as if their light is being collected and re-emitted. And so far, nothing confirmed. No unmistakable radio beacon, no clear artificial pattern, no probe waving back at us from the shadows, no mega-engineering signature that stands up to scrutiny, no cosmic construction project so obvious that it forces us to accept, without doubt, that intelligence has been here. This absence deepens the paradox, because it's not just that we haven't heard a greeting, it's that we haven't stumbled across the kind of debris that time should leave behind. Of course, our searches are imperfect. We have listened for only a short time. We have examined only a thin slice of the sky with the sensitivity we would truly want. There are many frequencies we haven't monitored well. Many signals could be brief, directional, or encoded in ways we don't recognize. A civilization might communicate with lasers, with neutrinos, with methods we haven't invented. They might be quiet by choice. They might live mostly in virtual worlds and have little reason to broadcast. And yet, the quiet still matters, because the Milky Way is not a small target, and cosmic history is not a short story. Even if communication is difficult, even if civilizations are rare, even if most never expand, it feels as though we should have found some kind of footprint by now. A region of space that looks tended. Instead, the sky looks natural. It looks as if the galaxy has been left alone. And that's where the simple explanations come in. The softer answers that try to soothe the discomfort. Maybe intelligent life is extraordinarily rare. Maybe Earth is a cosmic lottery winner. Maybe the steps from chemistry to biology, from biology to complex cells, from complex life to intelligence, are so unlikely that it has only happened once in this entire galaxy. Or maybe civilizations are common, but they are too far away. Space is vast, and even at light speed, it takes time. Perhaps the nearest technological society is on the other side of the Milky Way, and their signals have not yet reached us, or are too faint to detect. Or maybe communication is fundamentally limited. Maybe radio is a brief phase, like a childhood habit, quickly replaced by quieter, more efficient technologies. Maybe the window during which a civilization leaks detectable radio noise is only a few hundred years, and the odds of two civilizations overlapping in that window are small. Or perhaps timelines don't align. Civilizations could rise and fall like sparks in a storm, never lasting long enough to meet. The galaxy could be full of histories that never intersect, each one isolated by time, not just distance. These explanations are not foolish. Some of them might be partly true. The universe does not owe us company, and it does not owe us convenience. But many of these answers, even when they sound reasonable, leave a lingering discomfort behind, because they don't always address the scale of the silence. They explain why we might not be in conversation. They explain why we might not have a neighbor close enough to wave at. But they struggle with the deeper expectation that given enough time, at least one civilization should have become long-lived and expansive, and that its existence should have changed the galaxy in ways that don't require a friendly chat to notice. Rarity can explain a lot, but can it explain everything? Distance matters, but distance is less intimidating when you have millions of years and machines that never need to sleep. Communication limits are real, but engineering, expansion, and energy use tend to leave traces. Non-overlapping timelines are plausible, but the galaxy's age is so large that it feels like there should have been overlap somewhere, sometime, and evidence left behind even after the voices went quiet. This is where the great filter starts to feel attractive, in a dark, gravitational way, because it doesn't merely say, maybe they're out there, but we can't hear them. It asks something sharper. It asks whether something is stopping civilizations from lasting, not just from reaching us, but from enduring long enough to become the kind of presence the galaxy cannot hide. In that frame, the Fermi Paradox shifts. It stops being a question about alien geography and becomes a question about alien mortality. Maybe civilizations arise more often than we think. Maybe the universe is not barren of intelligence. Maybe on countless planets, life crawls out of the ocean, looks up at the stars, invents language, invents tools, invents fire, invents machines. Maybe there are many beginnings, but perhaps the endings come quickly. Perhaps the typical story is not one of endless ascent, but of brief illumination, followed by collapse, silence, and ruin. In that possibility, the galaxy could be full of civilizations that made it to radio, made it to industry, made it to the threshold of spaceflight, and then failed. Not all in the same way, not all at the same moment, but often enough that long-lived, galaxy-shaping expansion almost never happens. And if that is true, then the haunting question becomes, what keeps happening? What is so hard about staying alive as a technological species? What is so difficult about crossing from a planet-bound civilization to a stable interstellar one? It could be self-destruction, war, runaway weapons, miscalculated risks. It could be ecological collapse, systems pushed too far, stability lost, recovery impossible. It could be technologies that grow too powerful too quickly, outpacing wisdom and restraint. It could be something we haven't imagined yet, some bottleneck in the physics of expansion, some hidden barrier in biology, some inevitable trap in the sociology of intelligent beings. And there's a psychological weight to this shift that's hard to ignore. Because where is everybody is curious, but what happens to everybody is unsettling. It suggests a graveyard rather than a frontier. It suggests that intelligence is not a triumphant solution the universe keeps rediscovering, but a fragile phase, a brief bloom in the long cold garden of space, a candle that more often than not goes out before it can light the next room. And now, gently, the paradox stops being about them. It becomes about us. Because we are not outside this story, looking in. We are inside it, living one of the timelines the universe is testing. Our planet has produced a species that can split atoms, edit genes, model climate, and send machines beyond the edge of the solar system. We have already stepped into the early chapters of technological power, the kind of power that can build, and the kind of power that can break. If the galaxy is silent because civilizations commonly collapse, then the silence is not just an astronomical observation. It is a warning, shaped like an absence. It means the test is real. It means there is a set of challenges that many intelligent species fail to pass, and that the universe does not soften the consequences for anyone who gets them wrong. The great filter, in this light, is not primarily an alien theory. It is a mirror. It asks whether survival is rare, whether longevity is rare, whether the step from intelligence to lasting, stable, outward-reaching civilization is far more difficult than we like to imagine when we look at our own progress and assume it will continue. And this is why the Fermi Paradox feels so disturbing. It takes the most expansive stage imaginable, the galaxy with its hundreds of billions of stars, and it gives us a quiet audience. It takes our dreams of a crowded universe and replaces them with stillness. And then it quietly suggests that the stillness may not be an accident. It may be the result of countless stories that began with curiosity and ended before the stars could ever know their names. And once the paradox becomes a question of survival, the next step is to ask whether the hardest barrier lies in the distant past or somewhere waiting in our future. If we imagine the universe as a vast ocean of time and space, then the great filter is the part of the journey where most voyages end. Not because the destination is impossible in a simple physical sense. The laws of nature allow atoms to assemble into molecules, molecules into cells, cells into minds, and minds into machines that can reach beyond their home world. Nothing in physics forbids it. And yet, the night sky remains quiet. The great filter is a way of naming that quiet. It's a hypothesis that says, Somewhere between a dead planet and a starfaring civilization, there is at least one step, so difficult, so unlikely, or so fragile, that almost no one ever passes it. And if that's true, then the galaxy can be filled with worlds, filled with chances, and still feel empty. To understand it, it helps to picture not a single door, but a ladder. A long ladder rising from chemistry into civilization. Each rung is a transition, a threshold where nature has to do something new. And at every rung, there is the possibility of a bottleneck, a place where progress slows to a crawl, or stops entirely. A lifeless planet is not just nothing. It can be rich with raw materials, oceans, minerals, lightning, volcanoes, hydrothermal vents. It can have complex chemistry happening everywhere, constantly, for billions of years. But chemistry alone is not life. Chemistry is motion. Life is motion that remembers. So one rung is abiogenesis, the first time a system becomes capable of making imperfect copies of itself, and letting natural selection begin its long, patient work. We don't yet know how easy that is. It might be common wherever conditions are right, or it might be so rare that it happened only once in Earth's entire history. It might require a perfect storm of environment and time, or it might require something we haven't even imagined yet, a particular mineral surface, a particular cycle of wet and dry, a specific chemical pathway that's statistically almost never found. If abiogenesis happens, the next rung is survival. Early life, if it was life at all, would have been delicate. A fragile set of reactions, vulnerable to changing temperatures, impacts, radiation, chemistry drifting out of balance. It's not enough to begin. You have to persist long enough to become robust. Then comes the era of simple cells. On Earth, single-celled life dominated for most of our planet's history. Not as a brief prologue, but as the main story. For billions of years, life was tiny, microscopic, quietly transforming oceans and air, shaping the planet without ever building a brain, or a tool, or a telescope. That alone is an important clue. The ladder may have many rungs, but some rungs may be so high that life can spend most of the age of a world pressed against them, unable to pull itself up. One of those towering rungs is the rise of complex cells, what we call eukaryotes. Cells with internal structures, with compartments, with a kind of organized complexity that makes larger bodies possible. On Earth, this may have involved an extraordinary event, one cell engulfing another, not digesting it, but turning it into a permanent partner, a merger that became mitochondria, the power plants inside our cells. If that sort of symbiosis is rare, if it requires a near miraculous alignment of conditions and compatibility, then the universe could be full of simple life that never climbs higher. And after complex cells, there is multicellularity. It sounds like a natural next step, but it is not guaranteed. Becoming many cells instead of one requires cooperation. It requires cells to specialize, to surrender their individual freedom, to coordinate growth and repair, to build bodies that can move and sense and survive. It requires rules. It requires internal policing, because the moment cells can multiply, some will try to multiply selfishly. Cancer is, in a sense, the shadow of multicellularity, the reminder that cooperation is always under pressure from betrayal. Even as multicellular life arises, intelligence is not an inevitable destination. Earth produced forests and reefs and armored fish and dinosaurs for hundreds of millions of years without anything building radios. Intelligence in the way we mean it, abstract reasoning, cumulative culture, language capable of storing and transmitting complex ideas, may require a very specific set of evolutionary pressures. A planet can teem with life and still never produce a species that invents mathematics. And even if intelligence appears, technology is another rung. Tool use is not the same as industry. A mind can be clever and curious and still never reach the point where it manipulates energy at large scales. Technology requires not just brains, but hands, or something like hands. It requires access to materials that can be shaped. It requires fire, or an equivalent control over energy. It may require a stable environment where knowledge can accumulate across generations, rather than being repeatedly erased by catastrophe. And then, even if a technological civilization begins, there is the final rung that matters most for the silence of the galaxy. Long-term survival, not just surviving as a species for a few thousand years, but enduring through the dangerous adolescence of power. Learning to manage energy, weapons, ecology, and social instability without collapsing. Learning restraint, learning coordination, learning how to stay alive long enough to become visible across interstellar distances. Seen this way, the Great Filter is not a single thing. It is the idea that somewhere on this ladder, one rung is missing for almost everyone. Or perhaps the ladder is coated in ice, and almost every climber slips before reaching the top. And that brings us to the deeper question. Is the Great Filter one impossible step, or many difficult ones? It's tempting to search for a single dramatic barrier, one terrifying gate in the dark, one moment where the universe says no. Perhaps abiogenesis is so unlikely that it almost never happens. Or perhaps the leap to complex cells is a once-per-galaxy event. Or perhaps the moment a civilization invents certain technologies, it reliably destroys itself. But probability has a quieter way of building walls. You don't always need a single impossibility. You can get the same outcome from a chain of merely unlikely steps. Imagine that each rung on the ladder has a decent chance of being climbed. Not tiny, not absurd, just not guaranteed. Maybe abiogenesis occurs on 1 in 10 suitable planets. Maybe complex cells arise on 1 in 10 worlds with simple life. Maybe multicellularity appears on 1 in 10 worlds with complex cells. Maybe intelligence appears on 1 in 10 worlds with multicellular ecosystems. Maybe technology appears on 1 in 10 intelligent species. Maybe long-term survival happens for 1 in 10 technological civilizations. None of those numbers sound outrageous on their own. Each one might even feel optimistic, and yet multiply them together, and the fraction that reaches the end becomes 1 in a million. That is the strange arithmetic of the Great Filter. Mild unlikelihood, repeated enough times, becomes near impossibility. A galaxy can have billions of planets and still produce almost no enduring civilizations, simply because the ladder is long. And in a way, the distinction matters less than we wish it did. Whether the filter is one towering cliff or 1,000 steep hills, the end result can look the same from our perspective. The sky remains mostly silent. The radio spectrum remains mostly empty. The ancient starlight carries no obvious signatures of vast engineering projects. We look out and see a universe that seems willing to grow life, and yet reluctant to keep it. This is where the meaning of rare success begins to settle in. Even if life begins often, even if the universe is generous with microbial sparks, it may still be miserly with civilizations that last. The path from the first replicating molecules to a society capable of surviving its own power may be so narrow that almost every lineage falls away. It wandered. It experimented. It stalled. It endured mass extinctions and near misses. It spent most of its time in forms that would never build a city. The fact that we are here now, able to ask these questions, is not just a product of time passing. It is the product of an unbroken chain of survival through countless contingencies. And if that chain is rare, then a quiet galaxy is exactly what we should expect. Not because the universe is empty, but because it is full of beginnings that never become endings. Full of worlds where life remains small. Full of biospheres that never produce minds. Full of minds that never build machines. Full of civilizations that flicker briefly, like candles in a wind, and then go dark. In that view, the silence is not a contradiction. It is a consequence, and it casts a certain emotional gravity over our own existence. Not in a loud way, not in a triumphant way, more like the feeling of standing on a cliff at night, realizing how far you can fall, and how improbable it is that you are standing here at all. Because the Great Filter is not just about aliens, it is about us. It matters intensely where the filter sits on the ladder. If the hardest steps are behind us, if abiogenesis is incredibly rare, or complex cells almost never arise, or intelligence is a once-in-a-galaxy event, then our existence is not just interesting, it is precious in a deep statistical sense. It would mean the universe can host life for eons, and still almost never produce a species that can understand the cosmos. It would mean that the fact you can hear these words, the fact that humans can look up and think, is an extraordinary outcome of cosmic history. In that scenario, the Great Filter would be mostly in our past. We would be the survivors of the hardest trials, the few who made it through the narrowest gates. And the future, while still uncertain, might be less haunted by inevitability. We would still face danger, of course, but we would not be marching toward a guaranteed trap. We would be carrying a rare flame forward into the dark. But if the filter is ahead of us, then the story changes. If the early steps, life beginning, cells becoming complex, ecosystems forming, intelligence arising, are relatively easy, then the universe may be filled with minds that awaken, look at the stars, and begin to build. And then, again and again, something happens. Something that prevents them from lasting. Something that keeps them from spreading, from enduring, from becoming a stable presence that fills the galaxy with signals. In that case, intelligence may be common, but survival may be rare. And that is a chilling thought, because it suggests a pattern, not a curse, but a natural tendency, a kind of evolutionary trap, where minds become powerful faster than they become wise, where technology grows faster than cooperation, where the ability to change a planet outpaces the ability to care for it, where curiosity lights the fuse, and no one learns how to put it out. This is why the great filter carries both comfort and dread in the same breath. The very same idea can make us feel lucky or warned. And that brings us to one of the strangest inversions in all of cosmic thinking. Usually, we imagine that finding life elsewhere would be reassuring. We picture a future probe dipping into an alien ocean and discovering microbes, and we imagine celebration. We imagine it as proof that we are not alone, proof that the universe is alive, and it would be extraordinary. It would be one of the greatest discoveries in human history. But under the lens of the great filter, even that beautiful discovery could carry an unsettling undertone. Because if we find very primitive life, simple cells, basic metabolisms, microbial mats on many worlds, it might suggest that the earliest rungs of the ladder are easy, that abiogenesis happens readily when conditions are right, that the universe naturally tends to produce living chemistry. And if that's true, then the silence of the galaxy becomes harder to explain by rare beginnings. It begins to point, instead, toward rare endings. A galaxy full of simple life, but empty of advanced civilizations, would imply that the hardest step comes later. That something blocks the ascent from biology to durable technology. That somewhere after microbes, after complex cells, after intelligence, there is a barrier that almost no one crosses. It is a quiet reversal of what we expect. The discovery of life might not only answer a question, it might sharpen another. It might move the great filter closer to us. And that's why the great filter can feel like it contains both relief and terror at the same time. If we find nothing, anywhere, it could mean we are rare and perhaps safe from a universal pattern of self-destruction. If we find life everywhere, it could mean the universe is fertile, and that the danger lies in what comes next. Not because life is doomed, not because extinction is certain, but because the statistics would whisper that many have started this climb and very few have finished it. And there is another layer still, one that makes the great filter even more subtle. The filter may not be the same for everyone. It's easy to imagine a single obstacle that every civilization hits, like a wall built into the laws of physics. But the universe rarely works that way. More often, it offers broad possibilities and then punishes fragility in 1,000 different forms. Different worlds have different hazards. Some may be bombarded by impacts for longer. Some may have unstable climates. Some may orbit stars that flare violently. Some may lack plate tectonics and the recycling of nutrients. Some may have too little land or too much. Some may have chemistry that makes certain pathways difficult. Some may be trapped tidally, half frozen, half scorched, living in narrow twilight bands. And even among civilizations that do arise, the failure modes may vary. One might collapse through ecological overshoot, another through internal conflict, another through a runaway technology, another through complacency, stagnation, or a slow loss of capability. Another might simply never develop the means to leave its planet, not because it cannot think, but because it cannot access energy-rich fuels, or because its environment makes fire impossible, or because its gravity well is too deep for early rocketry. In that sense, the great filter may be less like a wall and more like a zone, a region of the ladder where risks cluster, where a civilization becomes powerful enough to harm itself, but not yet stable enough to avoid doing so, where the tools that can build a future can also erase it, where small mistakes can scale into irreversible outcomes. Some climbers may slip early, some may slip late, some may never even find the ladder. and the end result from far away still looks like silence. It may be a single overwhelmingly unlikely event, or a chain of narrow transitions, or a shifting landscape of recurring dangers that catch different species in different ways. And that prepares us for the next question, the one that matters most for our place in the story. If the Great Filter is real, then we want to know whether it is mostly behind us, in the deep past of biology, or ahead of us, in the future of technology. We want to know whether the universe is quiet because almost no one ever becomes intelligent, or because almost no one survives being intelligent for very long. But before we worry about the dangers of advanced civilizations, we have to ask whether reaching intelligence was already the rarest miracle of all. If reaching intelligence was already the rarest miracle of all, then the Great Filter may not be waiting out there in our future. It may be buried far behind us, in the deep, ancient layers of Earth's history, in events so old and so quiet that no mind was there to witness them. And in that possibility, there is a strange kind of hope, because it suggests that what's truly uncommon in the cosmos is not a spacefaring civilization, but a living world that manages step by step to become the kind of place where a thinking species can even appear at all. The first mystery in that chain is life's beginning. We have names for the ideas, and we have clever experiments and beautiful chemistry, but when you strip it down to the essential question, it becomes almost unsettling in its simplicity. How does a planet full of non-living molecules become a planet with something that can copy itself, that can store information, that can undergo selection, that can, in some meaningful sense, begin to fight against the drift toward disorder? Abiogenesis is one of the deepest unknowns in science, not because scientists haven't tried, but because the problem is so vast. It spans chemistry, geology, planetary environments, and time. It asks not just what life is made of, but how made of becomes alive. On Earth, the evidence suggests that life appeared relatively quickly after the planet cooled enough to have stable oceans. Depending on which lines of evidence you emphasize, you can get different dates, different levels of confidence, but the broad picture remains. Earth formed, endured its violent early era, and then, surprisingly soon, something like life was already here. That sounds like good news at first. Quick emergence could imply life is easy, that given water, energy, and a few useful ingredients, chemistry naturally climbs toward biology. It's a tempting thought, and it's one reason the search for life beyond Earth feels so plausible. But there's a quiet trap in that reasoning. We have one example, one planet, one history, one outcome that we're trying to interpret from the inside. And when you only have one data point, quick can be misleading. It might be that life truly is common, and Earth is simply a typical case. Or it might be that life is unbelievably rare, and Earth is one of the very few worlds that ever rolled the right numbers early enough. Because there's another factor that matters: time. If life took too long to begin here, we wouldn't be having this conversation. A planet has only so much stable time. Its star brightens, its geology shifts, its atmosphere changes. A world might be habitable for billions of years, but not forever. So if abiogenesis is extremely difficult, then on the rare worlds where it does happen, it may tend to happen early. Simply because early is the only way it can happen at all, and still leave time for everything else. In other words, the speed of life's appearance on Earth doesn't automatically prove that life is easy. It may only prove that on the one world where it did happen, it happened in time. And that makes the origin of life a powerful candidate for a bottleneck, perhaps even the bottleneck. If the Great Filter is here, then the universe could be filled with planets that look promising from afar. Oceans, continents, weather, volcanic plumes, lightning storms, an endless churn of organic molecules, but no spark that ever crosses the threshold into true self-replication, heredity, and evolution. Worlds that are almost alive, and yet remain forever chemical. But suppose life does begin. Suppose microbial life is not the rarest miracle. Even then, the next steps may not be guaranteed, because Earth, for most of its history, was not a world of forests and animals and coral reefs. It was a microbial planet, for a vast stretch of time, longer than the age of complex life by an almost embarrassing margin. The dominant forms of life were single-celled organisms. They spread through oceans, coated shorelines, inhabited sediments. They diversified into countless metabolic strategies. They became exquisitely adapted to nearly every environment Earth could offer. And they did all of it without building bodies. From our human perspective, it's easy to see single-celled life as a beginning, a primitive stage, a warm-up before the real story starts. But the planet didn't treat it that way. For billions of years, single-celled life was the story. It wasn't struggling to become complex in any obvious sense. It was thriving, it was stable, it was successful, which raises a quiet, uncomfortable question. If simple life is common in the universe, is it possible that simple life is where most living worlds stay? Because the leap from simple cells to complex cells may be one of the strangest transitions in all of biology. On Earth, complex life as we know it depends on eukaryotic cells, cells with internal structures, with organelles, with a nucleus that protects and organizes genetic material. Eukaryotes are the foundation of plants, animals, fungi, and all the multicellular abundance we see around us. And yet, eukaryotes arrived late, and once they arrived, they didn't appear to arise repeatedly in many independent ways. The evidence points towards something more unusual, an event that may have happened only once, a deep partnership, a merger. Long ago, one simple cell engulfed another, and instead of digesting it, kept it. Or perhaps the smaller cell invaded and made itself indispensable. Over time, the relationship became permanent. The smaller cell evolved into mitochondria, tiny power plants inside the larger cell, producing energy far more efficiently than most bacteria can manage alone. This one innovation may have changed the energetic budget of life itself. It may have allowed genomes to grow larger, cellular machinery to become more elaborate, and biological complexity to become sustainable. But think about what that implies. If complex cells required a rare symbiosis, a specific kind of cellular merger, a delicate evolutionary negotiation that succeeded only once in Earth's entire history, then complex life may not be an automatic consequence of biology. It may be a special case. And the long-era single-cell dominance begins to look less like a delay and more like a warning. The universe might be full of planets with bacterial oceans, full of microbial mats and drifting plankton-like cells, full of living chemistry that never crosses the threshold into complex architecture. Not because it isn't trying, but because evolution doesn't aim. It doesn't climb a predetermined ladder. It explores what works, what survives, what reproduces. And if simple cells work extremely well, then simple cells may persist indefinitely. In hindsight, complexity feels inevitable because we are complex. We look backward and see a path leading toward ourselves. As if the entire history of life was a long preparation for the arrival of minds and machines. But that's not how evolution experiences time. Evolution has no foresight, no destination. It has only the immediate arithmetic of survival and reproduction. And complexity, far from being a guaranteed upgrade, can be costly. More parts mean more points of failure, more energy required, more vulnerability, more dependence on stable environments. So the rise of eukaryotes, if it truly was a rare and difficult step, becomes another possible great filter hidden in the past. And even if complex cells emerge, even if the machinery of eukaryotic life begins to flourish, there is still another threshold ahead, another long, quiet wait written into Earth's history. Multicellular life. It's tempting to imagine multicellularity as a simple extension of single cells. Just stick together, specialize a little, and you're on your way to becoming an animal or a plant. But Earth doesn't tell the story that simply. For most of the planet's timeline, life remains small, microscopic, unseen by any eye, because eyes did not yet exist. The oceans were alive, yes, but they were not crowded with swimming creatures. The land was not green. The sky did not echo with wings. For billions of years, the world was dominated by organisms that would fit on the tip of a needle. Then, relatively late, astonishingly late, considering how long life had already existed, multicellular organisms began to appear. Bodies made of many cells working together. Cells that surrendered their individual reproduction for the success of the whole. Systems of communication, transport, support, defense. The first steps toward tissues, organs, and the elaborate choreography of animal life. And again, the delay itself becomes meaningful. If multicellular life were easy, if it were a natural, almost inevitable consequence of having complex cells, why did it take so long? There are possible answers, and none of them are simple. Perhaps the environment needed to change. Perhaps oxygen levels had to rise to support energy-hungry bodies. Perhaps nutrients, climate stability, and ecological interactions had to reach a certain balance. Perhaps predators were needed to drive innovation, or perhaps the absence of predators kept ecosystems stable and slow to change. But from the point of view of the Great Filter, the details all point in the same direction. Major transitions may be hard, not impossible, not mystical, just statistically rare and dependent on a delicate combination of conditions. It might be that multicellularity requires not just the genetic toolkit to coordinate cells, but also the right ecological pressures to make cooperation worth it, the right environmental stability to allow experiments to persist long enough, and the right energy availability to power larger bodies. And if that's true, then many living planets could remain in a state that is biologically rich, even beautiful in its own way, but forever simple. A world with oceans full of microbes could be alive for billions of years and still never produce anything like an animal. It could have evolution, adaptation, competition, and innovation, and yet never reach a stage where intelligence becomes possible. And even on Earth, once multicellular life arrived, it didn't immediately produce minds. It produced abundance, variety, strange forms, entire kingdoms of life that never needed brains at all. Which brings us to the next, perhaps most humbling idea of all. Intelligence is not the default outcome. When we look at Earth, we see one species that built radios, telescopes, and rockets. One species that mapped the genome, split the atom, and learned to read the faint background glow left over from the birth of the universe. And it's easy, almost automatic, to treat this as the point of evolution, as if intelligence were the natural destination toward which life tends to drift. But Earth's own record disagrees. Most life on this planet, across most of its history, has not been technologically intelligent. Not even close. Not because it failed, but because it succeeded in other ways. Bacteria and archaea are among the most enduring and adaptable forms of life we know. Insects have conquered nearly every environment on land. Plants reshaped the atmosphere and the surface of continents. Fungi built invisible empires beneath our feet. Ocean life flourished in forms that have persisted for hundreds of millions of years with no need for technology. Even among animals, intelligence in the human sense is not a common endpoint. Many lineages thrive with nervous systems tuned for specific tasks: navigation, hunting, camouflage, social coordination, without crossing into the realm of abstract language, mathematics, and tool building that compounds across generations. Evolution selects for what works now, and in most environments, what works now is not a species that invents engines. A mind like ours is expensive. It consumes energy. It requires long development. It often depends on social structures, learning, and extended care of offspring. It can create anxiety, distraction, and risk-taking. It can become trapped in its own perceptions. It can suffer, and it can be unnecessary. So when we see intelligence appear on Earth, we shouldn't assume it was inevitable. We should consider that it may have been contingent, a side path that happened to open, under specific circumstances, in one lineage of primates, on one continent, on one planet. Even the traits that seem obviously helpful for technology, dexterous hands, complex vocal communication, long lifespans, social learning, are not guaranteed to assemble in the same place at the same time. They are scattered across the tree of life like separate puzzle pieces. And sometimes, even when a creature is intelligent in many ways, able to solve problems, use tools, communicate, recognize itself, it may still be constrained by its environment or anatomy. A brilliant mind underwater has no easy access to fire. A brilliant mind without manipulators may struggle to build. A brilliant mind without long-lived culture may not accumulate knowledge fast enough. So perhaps the Great Filter is not just the origin of life, or the origin of complex cells, or the origin of multicellular organisms. Perhaps it is the origin of technological intelligence. Not intelligence in the broad sense of learning and adaptation, but the specific kind that builds a civilization capable of sending signals into space, capable of altering its planet, capable of dreaming beyond its own sky. If that step is rare, then the silence of the cosmos becomes less frightening. It becomes understandable, because the universe could be full of life that never speaks. Full of worlds with oceans, forests, and ecosystems, where evolution explores endlessly, but never produces a species that builds radio transmitters or interstellar probes. Not because such minds are forbidden, but because they are simply not favored often enough to become common. And yet, even if intelligence is rare, we might ask why. Was Earth unusually well suited for the long chain of transitions that led here? Was our planet, in some subtle way, an especially fertile cradle for complexity? It's dangerous to be too confident about this. With only one inhabited world to study, it's easy to overfit the story, to take every feature of Earth and declare it essential. But it's also possible that Earth really is unusual in ways that matter. Consider plate tectonics. Earth's surface is not a single unbroken shell. It's a set of moving plates that collide, separate, dive beneath each other, and recycle material between the crust and the mantle. This movement reshapes continents and ocean basins. It builds mountains and opens seaways. It drives volcanism and helps regulate carbon dioxide over geological time, acting like a thermostat that can stabilize climate. If a planet lacks plate tectonics or has a different style of geology, its climate regulation might be less forgiving. It might swing between extremes more easily, or become locked in a state that's technically habitable, but not stable enough for long-term evolutionary experimentation. Then there's Earth's magnetic field. Generated by the motion of molten metal in the core, it wraps the planet in an invisible shield that deflects much of the solar wind. Without it, a planet's atmosphere may be eroded over time, especially if it orbits an active star. Mars, smaller and colder, lost much of its magnetic protection and much of its atmosphere, leaving a thin, fragile envelope and a surface exposed to radiation. A magnetic field may not be required for life to exist, but it might help life persist, and persist long enough for complexity to arise. And then there is the Moon, large, close, and stabilizing. Earth's moon influences tides, which may have helped early chemistry in coastal zones by cycling wet and dry environments. More importantly, it stabilizes Earth's axial tilt, helping prevent chaotic swings in climate over long timescales. Again, none of this is proven as a requirement. But when you're looking for reasons why Earth might have been unusually steady, unusually supportive, the Moon is difficult to ignore. Add to that long-term climate stability, not perfect, not gentle, but stable enough. Earth has endured ice ages, greenhouse periods, mass extinctions, and asteroid impacts. And yet, despite all of it, the planet remained a place where liquid water could exist on the surface for billions of years. That kind of sustained habitability may be rarer than we'd like to believe. And chemical richness matters too. Earth has a diverse inventory of elements and compounds, and it has active cycles that move them around: carbon, nitrogen, phosphorus, sulfur. Life doesn't just need water and warmth. It needs chemistry that can build complexity and keep it going. It needs nutrients, gradients, energy sources, and environments where molecules can concentrate and react. A planet can sit in the so-called habitable zone and still be missing crucial ingredients, or still be too geologically quiet, or too chemically limited, or too unstable. So perhaps Earth is not merely habitable. Perhaps it is unusually habitable, not in a romantic sense, but in a statistical sense. A world where multiple stabilizing factors happen to align. A world that stayed wet, temperate, and chemically active long enough for life not just to exist, but to evolve through a sequence of difficult transitions. And if that's true, then the Great Filter may be behind us in more ways than one. It may not be a single wall that life crashes into. It may be a whole landscape of narrow passages, and Earth happened to find a path through them. Abiogenesis, complex cells, multicellularity, large bodies, nervous systems, social learning, language, tool use, fire, agriculture, industry, science. Each step plausible on its own, and yet when multiplied together, perhaps vanishingly rare. And this is where the idea becomes emotionally powerful. Because if the Great Filter lies in the past, if the hardest steps were the ones required to produce a technological species at all, then our situation changes. The silence of the universe would not necessarily be a warning that advanced civilizations inevitably self-destruct. It could simply mean that most worlds never produce a civilization in the first place. In that scenario, humanity is not standing at the edge of an unavoidable cliff. We are standing on an improbable peak we somehow climbed, perhaps without realizing how steep the path truly was. That doesn't mean the future is safe. It doesn't mean progress is guaranteed. It doesn't mean we can ignore risks. But it does mean something important. It means that our story might not be a short one by cosmic law. If the filter is behind us, then the future is open. Still dangerous, yes, but not fundamentally doomed. Not a universal pattern, where every civilization reaches a certain level and then vanishes like a brief spark in a cold wind. For many people, that possibility is comforting, even if it's also humbling, because it turns the fear outward into awe. Instead of imagining a galaxy full of dead civilizations, we imagine a galaxy full of quiet worlds, some lifeless, some microbial, some complex but wordless, each beautiful in its own right, but lacking that rare combination of circumstances that produces a species capable of asking questions into the dark. And it gives our existence a different kind of weight, not the weight of impending doom, but the weight of responsibility. If we are rare, then what we do matters more, not less. If we are among the first, or among the few, then the universe is not crowded with replacements. There may be no chorus of older voices to guide us, no interstellar community waiting for us to join. Just us and the silence. And in that silence, the idea of an ancient filter can feel like a gentle answer, a soothing explanation that lets us breathe. The cosmos is quiet because the climb is hard, because the ladder has missing rungs, because the path from chemistry to culture is so narrow that even a galaxy with hundreds of billions of stars might produce only a handful of civilizations, scattered across time and distance so widely that they never overlap.
It's a hopeful interpretation, in its own strange way.
But hope here comes with a shadow, because even if the hardest steps are behind us, even if we are the beneficiaries of an almost impossibly lucky evolutionary history, there is still the question we postponed. The one that waits patiently at the edge of every comforting thought. What if the silence is not just about rarity? What if it's about survival? Because the comfort of an ancient filter fades quickly, once we consider the possibility that intelligence survives only long enough to build the tools of its own destruction. And if that is true, then the moment a world becomes truly intelligent may also be the moment it steps onto thin ice. Because intelligence is not just the ability to understand nature, it is the ability to rearrange nature, to take the ancient rules of chemistry and physics and bend them into new shapes. Fire into furnaces, stone into cities, atoms into energy, information into influence. And that's the unsettling symmetry at the heart of this idea. The same mind that learns to cure disease can learn to create it. The same curiosity that builds telescopes can build weapons that reach across continents. The same talent for prediction and planning can be used to stabilize a society or to exploit it. In the earliest chapters of a civilization, danger is mostly local. A storm, a drought, a predator, an earthquake. Tragedy can be immense, but it tends to stay contained by geography and by the limits of what a species can do. But as capability grows, something changes. The threats stop being only external. They become internal. They come from decisions, from systems, from accidents in labs, from miscalculations made at high speed, from chains of events no individual intended. A young technological society can become fragile precisely when it becomes powerful, because the number of ways it can fail multiplies faster than the number of ways it can protect itself. It builds interdependence. It concentrates energy. It ties food to supply chains to electricity, electricity to complex machines, and complex machines to policies and trust. And then, over time, it accumulates tools that can act on planetary scales, while the minds using them remain shaped by the same ancient instincts that evolved to survive savannas and forests. The capacity to affect the whole world arrives long before the emotional and political maturity to govern that capacity wisely. So maybe there is a threshold, not of intelligence, but of instability, a point where a civilization's power begins to outrun its wisdom, its coordination, and its restraint, a point where a species becomes capable of ending itself, long before it becomes capable of lasting. If such a threshold exists, it would not need to be perfectly consistent. It would not have to strike every time, in the same way, on every planet. It would only need to happen often enough that the galaxy becomes quiet. And on our world, we have already seen the first clear outline of what that threshold can look like. Nuclear weapons were, in a way, the first time humanity held a lever connected to its own extinction. Before that, wars were horrific, but limited by the human scale. Armies had to move, supplies had to travel, violence had friction. Even the worst conflicts could not easily erase the entire species or collapse the biosphere in an afternoon. Then, Within a few decades, we crossed a line. We learned to unlock the binding energy in atomic nuclei and to release it as a flash brighter than the sun, hotter than the center of the star, concentrated into a single moment. We discovered a fire that does not need oxygen, a fire that can burn cities into shadows, and what is so eerie about this achievement is how quickly it arrived. In cosmic terms, it was instantaneous, a blink between the first radio broadcasts and the first mushroom clouds. A civilization can go from inventing flight to possessing doomsday devices in less than a century. That suggests a troubling pattern. A species may gain the power to destroy itself before it gains what you might call durable planetary maturity, before it learns how to manage fear without panic, before it learns how to compete without annihilation, before it develops institutions that can survive stress, misinformation, and the temptation to strike first. Nuclear war is often imagined as a deliberate act, a villain pressing a button. But history has shown something more subtle and more frightening. Close calls, misunderstandings, false alarms, systems that nearly escalated because a radar glitched, because a signal was misread, because a decision had to be made in minutes. The danger is not only malice. It is also error. It is also the brittle nature of deterrence. The idea that peace can be maintained by the promise of mutual ruin as long as everyone behaves perfectly. Forever. And even if a civilization avoids total nuclear extinction, the after effects could still be terminal for its long-term trajectory. A large exchange could collapse global trade, agriculture, governance, and trust. It could fracture the scientific and industrial base that took centuries to build. It could push societies into long periods of scarcity and conflict, where recovery becomes harder each year. The deeper point is not only about nuclear weapons themselves, it's that they offer a template. They show the shape of a future risk, a technology that is incredibly powerful, relatively compact, and once discovered, difficult to uninvent. A technology that does not require a planet to be evil, only to be fallible, only to be divided, only to be unlucky. And in that sense, nuclear weapons might be just the first example of a broader class of self-inflicted civilizational dangers that emerge as a species climbs the ladder of capability. Not all of those dangers come with bright flashes. Some of them come quietly, through the slow destabilization of the very environment that made civilization possible in the first place. A technological society doesn't just live on a planet. It rewires it. It pulls carbon from ancient rocks and releases it into the air. It drains wetlands and redirects rivers. It clears forests that once held soil in place and moderated rainfall. It spreads chemicals and plastics through ecosystems that never evolved to process them. It harvests oceans with industrial efficiency, removing life faster than it can replenish. And it does all of this not because it wants to destroy its home, but because it wants to grow, to feed billions, to provide comfort, to build, to compete, to keep the lights on. The danger is that a biosphere is not an infinite reservoir. It is a complex dynamic system balanced by feedback loops, some stabilizing, some amplifying. When a civilization pushes too hard, too fast, it can trigger changes that cascade. Climate change is one of the clearest examples, not as a single event, but as a shifting baseline. Heat waves become more common, rainfall patterns drift, droughts lengthen, storms intensify, ice melts, seas rise, coastlines erode. Agriculture, so dependent on stable seasons, finds itself gambling each year with unfamiliar odds. But the true risk is not only the climate itself, it's the way climate stress threads through everything else. And unrest grows, migration increases, and politics hardens. Infrastructure is strained by floods, fires, and heat. Insurance becomes impossible in certain regions. Governments spend more on emergency response and less on long-term stability. Trust erodes, and in that erosion, cooperation becomes harder, exactly when cooperation is most needed. There is also the quiet unraveling of biodiversity, species disappearing, pollinators declining, fisheries collapsing, soils thinning, forests losing resilience to pests and drought. These losses can seem abstract, like background noise, until they cross thresholds where ecosystems no longer function the way civilization expects them to. And what makes this kind of collapse especially haunting is that it doesn't have to be dramatic to be terminal. A civilization doesn't need to be wiped out to fail the test of the stars. It might simply lose its momentum. It might fall into repeated crises that consume its resources and attention. It might become too busy surviving to invest in exploration, too fractured to coordinate large projects, too politically unstable to sustain long-term scientific institutions. From the inside, such a decline might feel like a series of manageable problems, a bad decade, then another, the gradual normalization of emergency. And then, one day, there is no longer the spare capacity to do ambitious things. No longer the surplus energy and peace required to build starships or to maintain the kind of global collaboration that interstellar life might demand. In this view, the filter is not necessarily a single blow. It can be a slow squeeze. And as technologies continue to advance, they may not only strain the physical environment, they may also create new kinds of instability within the civilization itself, which brings us to a threshold that feels both inevitable and uncertain: the rise of artificial intelligence. It's easy to speak about AI in extremes, either as salvation or doom. But for a calm scientific mind, the most realistic picture is often more nuanced and more unsettling precisely because of that nuance. Advanced AI is not one invention. It is a general amplifier. It can amplify productivity, discovery, and problem solving. It can accelerate medicine, engineering, and climate modeling. It can help manage complex systems that are too intricate for humans to oversee directly. But it can also amplify competition, surveillance, persuasion, and conflict. And the core concern here is not that machines become evil in a human sense. It is that optimization without alignment can be dangerous. A powerful system that pursues a goal relentlessly can cause harm if the goal is poorly specified, if the system learns unintended shortcuts, or if it reshapes the world to make its objective easier. In small systems, these failures are annoying. In large systems, they can be catastrophic. Misalignment is one part of the risk. Another is concentration of power. If advanced AI becomes controlled by a small number of institutions, governments, corporations, or factions, then the balance of society can shift. Those who control the systems may gain unprecedented influence over information, economics, and behavior. And even if they mean well, the temptation to use such power for security, dominance, or stability can be overwhelming. Stability, in that context, can become a cage. There is also the risk of automated conflict. When decision-making speeds up, when cyber operations and drones and defenses are guided by algorithms, the time available for human judgment can shrink to seconds. In a tense world, systems could escalate faster than diplomacy can respond, not out of hatred, but out of feedback loops. And then there is the problem of loss of control, not necessarily a sudden rebellion, but a gradual dependence. A civilization may hand more and more of its critical functions to systems it does not fully understand: financial markets, power grids, military early warning, supply chains, medical diagnostics, governance itself. At first, this feels efficient. It feels safe. It feels like progress. But over time, it can create a brittle reliance, a world where humans can no longer easily intervene because the system has become too complex, too fast, too deeply embedded. A world where failure is not localized, but systemic. Again, it's important not to drift into pure speculation. We don't know how AI will develop. We don't know whether advanced systems will be controllable, or whether they will stabilize society rather than destabilize it. But as a candidate for a great filter, AI has a certain chilling logic. It is a multiplier of both capability and consequence. It could allow a civilization to solve problems that would otherwise destroy it, or it could allow a civilization to create problems it can no longer contain. And perhaps the most unsettling part is that the transition could happen quickly, faster than cultural adaptation, faster than legal frameworks, faster than the slow evolution of norms. A species might find itself almost suddenly living alongside intelligence it created, without having fully decided what it wants the future to be. And if AI is one kind of amplifier, biotechnology is another, one that operates not on code and computation, but on life itself. For most of history, biology was something that happened to you. You could breed plants and animals, yes, and you could practice medicine with varying degrees of success, but you could not easily rewrite the machinery of living cells. Now, that has changed. Tools for genetic editing, synthesis, and laboratory automation are becoming more powerful and more accessible. The barriers to entry, cost, expertise, equipment continue to fall over time. And that shift creates a new category of risk. Threats that are not necessarily large, expensive, and centralized, but cheap, decentralized, and hard to contain. An engineered pathogen does not need a missile. It does not need a fleet. It can travel invisibly through airports, through cities, through the ordinary closeness of social life. It can spread before anyone realizes what it is. It can mutate. It can hide in mild cases and emerge later. It can target vulnerabilities in ways nature never tried. This is not to say such a catastrophe is inevitable. Biology is complicated. Engineering a world-ending organism is not trivial, and humanity has strong incentives to develop defenses, vaccines, surveillance, rapid response, better indoor air, better public health. But as a filter candidate, biotechnology has a particular pattern that repeats the theme we've been circling. Sophistication can create fragility. As civilization becomes more connected, more mobile, more dependent on stable health systems, and at the same time, the tools that could disrupt those systems become more widespread. In earlier eras, only states could wage catastrophic war. In a future era, small groups, or even lone actors, might gain access to capabilities once reserved for nations. And even without malice, accidents matter. A lab mistake, a containment failure, a research program pursued too aggressively could unleash something the world is not prepared to stop. The galaxy may be full of planets where life became clever enough to edit itself before it became wise enough to do so safely. And through all of these examples, nuclear fire, environmental destabilization, intelligent machines, engineered biology, there is a common thread. It is not simply that technology is dangerous. It is that technology changes the shape of risk. It turns rare disasters into plausible ones. It turns local mistakes into global consequences. It turns short-term incentives into long-term traps. It creates power that demands coordination in a species that may not yet be good at coordinating. But even this picture of dramatic catastrophes might be too simple, because a great filter does not have to look like an apocalypse. It could be slow, quiet, almost comfortable. A civilization might not end in explosions. It might simply stop. Imagine a world where the first burst of scientific progress slows, not because knowledge is exhausted, but because society turns inward, because fear of instability leads to rigid control, because surveillance becomes so complete that dissent and experimentation fade, because the safest political strategy becomes preserving the present rather than risking the unknown. An authoritarian lock-in does not need to be cruel in obvious ways to be effective. It can be soft, bureaucratic, normalized. It can promise security and predictability. It can remove the chaos of open societies, along with their creativity. Over generations, the culture of exploration can dim. The idea of reaching to the stars can become quaint, even suspicious. Or consider stagnation through comfort. A civilization may reach a level of abundance where the incentives to expand vanish. Virtual worlds, endless entertainment, engineered pleasures, enough to keep people content, enough to keep them indoors, enough to make the physical universe feel distant and unnecessary. From the inside, this doesn't feel like collapse, it feels like success, but the stars remain unvisited. There are other slow filters too. Infertility collapse, whether through lifestyle changes, economic pressure, cultural shifts, or biological factors. A steady decline in population that reduces dynamism and concentrates resources into maintaining aging systems rather than building new ones. Resource exhaustion is another, not in the simplistic sense of running out, but in the sense of diminishing returns. Easy resources are harvested first. What remains is harder to obtain, requiring more energy, more complexity, more coordination. The society becomes a machine that must keep running just to stay in place. If it stumbles, recovery becomes increasingly difficult. And then there is the possibility of permanent civilizational decline without extinction. A world can remain inhabited, even technologically capable in small ways, but stuck below the threshold needed for interstellar expansion. Perhaps it loses industrial capacity. Perhaps it loses the ability to produce advanced materials. Perhaps it loses the global cooperation required to sustain space infrastructure. Perhaps it becomes trapped in cycles of regional conflict and rebuilding. If this happens often, the galaxy could be filled with planets where intelligent beings look up at the stars and wonder the same thing we wonder, not knowing that their own world is already slowly becoming quieter. In this slow filter scenario, the great filter is not a single gate that slams shut. It is a long corridor, lined with doors that gradually close. Each one seems manageable. Each one is rationalized. Each one is survived, until, eventually, the path to the stars is no longer open. And the most unnerving part is that from the inside it might not feel like failure at all. It might feel like normal life. It might feel like the future is still ahead, even as the window narrows. So when we ask whether the filter lies ahead of us, we are really asking a deeper question. Can a technological civilization become not only intelligent, but wise? Can it build tools without building traps? Can it hold immense power without becoming brittle? Can it coordinate at planetary scale, across cultures and borders, through fear and misinformation and competition, long enough to become something stable, enduring, and expansive? Because if the answer is no, not just for us but for most worlds, then the silence around us begins to take on a different kind of meaning. Not emptiness, not rarity, but repetition. A pattern of brief bright moments, civilizations that awaken, accelerate, and then vanish, or fade, or stall, before they ever learn to cross the deep ocean between the stars. And if advanced civilizations really do tend to fail, then the next question is even stranger. Could the silence of the galaxy be the fossil record of countless brief awakenings? If the silence of the galaxy is a kind of fossil record, then it may not be made of bones or stones, but of timing, of short-lived sparks, of civilizations that for a moment become loud enough to be noticed, and then go quiet again, long before their light could ever spread across the Milky Way in a way that would be obvious to anyone watching from afar. It's possible that most technological species have a very small window where they are in any practical sense visible. Think about our own world. For nearly all of human history, Earth was indistinguishable from any other living planet at a distance. We had fire, language, culture, art, agriculture, and none of it would carry across the interstellar dark. Then, in just over a century, we began to leak radio waves into space. We began to reshape the chemistry of our atmosphere. We began to place bright, fast-moving objects in orbit. And yet even now, our signature is fragile. Our loudest broadcasts are not necessarily continuous. Many of our most powerful transmissions are narrow beams, aimed at specific targets, and not sweeping the galaxy like a lighthouse. Our technological phase as a detectable phenomenon may be thinner than we like to imagine. Now widen the lens. Imagine a planet where intelligence arises and builds machines, but only for a short time. A few centuries, a few thousand years, maybe even just a few generations of industrial power before a collapse, a regression, a self-imposed quieting, or a shift into technologies that do not leak much into space. A civilization that burns brightly, but briefly. In that scenario, the galaxy could host not just a handful of intelligent species, but thousands, millions even. A long parade of awakenings, scattered across billions of years, and still the sky could look exactly like it does now. Because visibility is not the same as existence. It is not enough to be intelligent. It is not enough to build cities and instruments and engines. To be noticed across the Milky Way, a civilization must be both loud and long-lived. It must remain in a detectable state for a very long time, relative to the scale of interstellar distances and the age of the galaxy. This turns the great filter into something that feels almost like a cruel calendar problem. Not only do you have to survive your own adolescence, you have to survive long enough for the universe to notice you. The Milky Way is more than 100,000 light-years across. That number is easy to say, but hard to feel. A signal traveling at the speed of light takes 100,000 years to cross it. If a civilization's detectable phase lasts only 1,000 years, then its broadcast bubble is a sphere only 1,000 light-years in radius. That sounds large until you compare it to the volume of the galaxy. It becomes a small, thin patch of time and space. The galaxy is not standing still. Stars orbit the center. Regions drift. What was near becomes far. What was aligned becomes scattered. So even if the Milky Way has been home to countless brief technological species, the odds that any two are loud at the same time and close enough to notice one another may be astonishingly low. The silence, then, would not be a verdict. It would be a symptom of misalignment, a timing problem, layered on top of a survival problem. To detect another civilization, two narrow windows must overlap. First, there is the window of existence, the period when a species is capable of generating a signal or building a structure that can be sensed over interstellar distances. Not just any technology, but the kind that leaves fingerprints in the cosmic dark. Second, there is the window of attention, the period when another civilization is actively looking, listening, and able to interpret what it finds. The overlap between those windows might be razor thin. Even on Earth, our listening has been brief. Modern radio astronomy is young. Our searches for artificial signals, deliberate, systematic searches, are younger still. We have only recently developed the sensitivity to detect faint transmissions from far away. We have only recently begun to imagine what a truly alien signal might look like beyond the simple idea of a repeating beep. And we are listening from a single point in space, with limited time, limited coverage, limited patience. Now imagine a civilization on the other side of the galaxy that reached a technological peak 2 million years ago and then vanished. Its radio leakage, if it had any, swept past our region of space long before we evolved ears to hear it. Its brightest industrial signatures may have come and gone, and the planet may have returned to a quieter equilibrium. Or imagine a civilization that exists right now, but is so far away that its signals have not yet arrived. If they are 10,000 light-years distant, then anything they transmit today will reach us 10,000 years from now. We are always looking into the past, but the past we see depends on distance. The galaxy is a patchwork of time. Distance does not merely separate places, it separates eras. And on top of that, communication itself may not be what we once pictured. We imagine civilizations broadcasting powerful omnidirectional radio waves, like a sphere of sound expanding endlessly. But an efficient civilization might not do that. It might use tightly focused beams. It might use frequencies we are not monitoring. It might communicate through methods that leave little trace in the electromagnetic spectrum at all. It might also choose silence, not out of fear necessarily, not out of malice, but simply because broadcasting is wasteful, because there is no obvious recipient, because energy is precious, because privacy is valuable, because the universe is vast and shouting into it is like shouting into a hurricane. So the overlap required for contact becomes even narrower. Not only must two civilizations exist at the right times and within the right distances, they must also be using compatible technologies, and one must be listening in the right way, and the other must be emitting something detectable in the first place. When you layer all of that together, the eerie quiet we experience begins to feel less like a contradiction, and more like what you'd expect from a galaxy full of short stories that rarely intersect. Silence does not necessarily mean no one ever existed. It may mean we are arriving late to a theater where the performances have already ended and the stage has been swept clean. And that brings us to an even stranger thought. If civilizations have risen and fallen across the Milky Way, then there may be ruins out there. Not romantic ruins, not stone temples beneath alien sunsets, but the kinds of leftovers a technological species might leave behind. Dead probes drifting between the stars, their power sources cold, long since punctured by micrometeoroids, slowly venting their atmosphere into nothing. Factories and satellites and stations, broken into debris by collisions in time. Perhaps even larger things. Not necessarily the grand, unmistakable megastructures of science fiction, but modest astroengineering. A rearranged asteroid belt, a partially dismantled planet, a star surrounded by a cloud of collectors that never reached completion. A civilization may begin to reshape its environment and then stop. A project may be left half-finished, like scaffolding around a cathedral that was never built. Or consider probes, small, smart, patient machines, sent out to explore, to map, to watch. A civilization might seed the galaxy with them, and then disappear. The probes could persist for a while, silent and waiting, until their systems degrade. Or they could remain in standby for millions of years, if built for endurance, hidden in cold orbits, conserving power like cosmic time capsules. It sounds like the beginning of a mystery, and it is, but the difficulty is almost painful, because detecting such traces is extraordinarily hard. Space is vast, and ruins are small. Even within our own solar system, we struggle to see everything. We track many asteroids, But not all. We have mapped Mars in detail, yet the planet still holds surprises. We have only begun to explore the moons of the outer planets, and the Kuiper Belt remains mostly unvisited. Now scale that challenge to the entire galaxy. A dead probe a few meters wide, drifting in interstellar space, would be essentially invisible unless it passed very close to us. An abandoned habitat orbiting a distant star might reflect starlight in a way indistinguishable from a natural object. Debris fields could look like dust. Subtle changes in a planetary surface could be erased by geology, buried under sediments, or softened by erosion and time. Even if a civilization built something big enough to affect the light of its star, something like a swarm of collectors or an engineered ring, nature has its own ways of making confusing signals. Dust clouds, star spots, and circumstellar debris can mimic artificial patterns, and our instruments, as powerful as they are, still see distant star systems as points of light, not as landscapes. We are trying to do archaeology from tens of thousands of light years away. We are trying to read a history book whose pages are scattered across the dark, written in a language we do not know, with most of the ink faded. So it may be that the galaxy is not empty. It may be that it is quiet in a different way. Not the silence of perfect loneliness, but the archaeological silence of a place where many lives have passed, and the evidence has become faint, fragmented, and hard to interpret. There is a kind of loneliness in that too, because it suggests that the universe might not be withholding life from us. It might simply be showing us what happens to life when it reaches for power and cannot hold it for long. And that leads to a subtle but profound shift in the question. Maybe the paradox is not primarily about origin. Maybe it is about endurance. It is one thing for a planet to produce intelligence. That alone is astonishing. Chemistry learning to think, matter arranging itself into minds that can look outward and ask why. But it is another thing entirely for that intelligence to remain stable for tens of thousands of years, or millions. Consider how brief our own stability has been. Human civilization, in the sense of large, complex societies, is only a few thousand years old. Our industrial age is a blink. Our global technological network is younger than many people alive today. And already, it has created pressures that reach into every ecosystem, every ocean current, every layer of air. We like to imagine a straight line, from primitive beginnings to advanced mastery, from early tools to starships. But perhaps the more realistic shape is jagged, bursts and stalls, periods of rapid growth followed by long quiet intervals, or resets. In that view, the rare achievement is not intelligence itself. The rare achievement is longevity. To last, a civilization must manage its own power. It must navigate internal conflict. It must survive environmental change, whether self-inflicted or natural. It must be resilient against disasters, pandemics, impacts, supervolcanoes, stellar flares. It must avoid the temptation to consume its foundations faster than they can be renewed. And beyond survival, it must maintain continuity. Knowledge must be preserved. Institutions must adapt without breaking. Technology must remain in balance with the world that supports it. A species can be brilliant and still be fragile. In fact, brilliance may increase fragility because it accelerates capability faster than wisdom. It gives a civilization the ability to transform its planet long before it fully understands the consequences. So the galaxy could be full of intelligent beginnings, each one a miracle, yet almost none become the kind of civilization that lasts long enough to expand, to leave enduring monuments, to become a permanent feature of the cosmic landscape. This is where the Great Filter becomes chilling in a new way. Not as a single wall that stops everyone at the same place, but as a long corridor lined with doors that most never reach, because they cannot keep walking for long enough. Longevity is not a moment. It is a practice, repeated across generations. And even if a civilization does endure, expansion may be harder than it looks. We often imagine interstellar colonization as a kind of inevitable wave. Once you have the technology, you spread. Once you spread, you fill the galaxy. And if that were easy and fast, then yes, the silence would be almost impossible to explain. But the universe is not obliged to match our simplest models. Interstellar travel is not like crossing an ocean. It is like crossing an ocean where the water is vacuum, the storms are radiation. The distances are so large that even the fastest ships take lifetimes. and every mistake is fatal. The energy costs are immense, the engineering demands are extreme. Life support must be closed-loop and reliable for years, decades, centuries. The smallest failure becomes a slow, quiet catastrophe. And then there is the psychology of distance. The further you go, the less connected you are to the origin. A colony becomes its own world, with its own priorities. It may not continue the mission. It may not want to. It may choose to turn inward, to perfect itself, rather than spread. Even if you imagined self-replicating probes, machines that could, in theory, hop from star to star and build copies of themselves, the reality could be more complicated. Replication requires resources, and resources require time to gather and refine. Mistakes accumulate, systems degrade. A probe that replicates too aggressively might become unstable or dangerous, prompting its creators to restrict it. Or perhaps the universe itself restricts it. Radiation damage, collisions with dust at high speed, the sheer complexity of autonomous manufacturing. Expansion could be slow. Expansion could be fragile. Expansion could be something that only the most stable, most patient, most long-lived civilizations can sustain. And yet, even with those limits, the long timescales still make the silence unsettling. Because the galaxy is ancient. If even a small fraction of civilizations endure for 1,000,000 years, and if even a small fraction of those attempt expansion, you might still expect some visible presence by now. Some unmistakable sign, some clear alteration of starlight, some beacon, some engineered pattern that cannot be confused with nature. Unless the enduring ones are rare, unless the corridor is longer than we think, and most travelers do not make it far, or unless the visible ones are quiet by choice, or invisible by design, or operating on principles we have not yet learned to detect. But even those possibilities do not fully soothe the mind. They change the shape of the mystery, but they do not remove it. They keep the pressure in place, like the deep ocean pressing against a submarine hull. Somewhere between no one ever existed, and everyone expands and fills the galaxy, lies a third possibility, a galaxy where life tries again and again, and mostly fails to last. A silent galaxy filled with failed beginnings. And when we return to Earth, when we step back from the abstractions and remember that we are not just observers, but participants, the view becomes quietly haunting. Because it reframes the night sky. Those stars are not just distant suns, they are potential cradles, possible laboratories, stages where chemistry could have learned to think, where eyes could have opened under alien skies, where someone could have built their first radio, their first rocket, their first dream of crossing the interstellar sea. And perhaps many did. Perhaps the Milky Way has hosted countless experiments in intelligence. Not designed experiments, of course, no guiding hand, no cosmic engineer, but natural experiments, repeated across time. Life emerges, evolves, becomes complex, becomes aware. And then it flickers, not always in a dramatic blaze, sometimes in a slow dimming. A civilization might not annihilate itself. It might simply lose the thread. It might retreat. It might become quiet. It might collapse into smaller societies that no longer build mega-projects or send signals into space. It might survive biologically, even culturally, but no longer be a technological force that changes the galaxy. From far away, all of those outcomes look the same. A brief bright phase, followed by darkness. So the silence we hear when we listen to the stars may not be the silence of an empty hall. It may be the silence after many songs have ended, an elegiac quiet, heavy with the possibility that the universe has been full of voices, and that most of them did not last long enough to be heard by anyone else. And if that is true, then the Great Filter is not merely a puzzle for astronomers. It is a mirror. Because we are right now in our own narrow window. We are one of those brief, bright moments, at least so far. We have reached the stage where our planet is changing under our hands, where our tools are powerful enough to shape the future of life on Earth, where our decisions echo farther than any generation before us could have imagined. In the cosmic sense, we are young. Loud in a small way, visible in a thin slice of time, and the galaxy is watching, if the galaxy ever watches at all, with the indifferent patience of physics. So when we look up and find no clear evidence of anyone else, it does not only raise the question of where they are, it raises the question of what happens next. If the Milky Way is filled with failed beginnings, then our task is not just to become advanced. It is to become enduring. Not just to reach for the stars, but to remain steady long enough that the journey is possible. Because the most unsettling thought is not that we are alone in the universe. The most unsettling thought is that we might not be alone, and that the reason we hear nothing is that survival at high power is rare. But if the great filter is real, then the question that matters most is no longer what happened to them, but what kind of future might allow us to escape the same fate. And that question, what kind of future might allow us to escape the same fate, has a strange way of turning the telescope around. Because the great filter isn't only out there, scattered among distant stars and hypothetical histories. It is also in here, in the choices a species makes when it first realizes it can reshape its world, and then, perhaps, reshape itself. In the stories we tell about cosmic achievement, we often imagine speed, the first signal, the first colony ship, the first city under an alien sky. We picture a civilization as a bright flare, an explosion of ingenuity that races outward, claiming the darkness with light. But the universe doesn't reward flares. In cosmic terms, greatness may have less to do with how quickly you rise, and more to do with how long you remain. A civilization becomes visible by enduring, not visible in the sense of a spotlight, but visible in the deeper way that time itself makes something undeniable. A species that lasts long enough doesn't just reach for the stars once. It tries again and again and again. It has the patience to build, to repair, to learn from failure, to repeat the slow labor of becoming. It is not defined by a single dramatic breakthrough, but by 1,000 quiet continuations. Because the dangerous transitions aren't always the ones that make headlines in a history book. Sometimes the real filter is not the moment you discover fire, or split the atom, or build a thinking machine. Sometimes the real test begins afterward, when the novelty fades, when the tools become ordinary, when power becomes cheap, and the question is no longer, can we, but what happens when everyone can? The most dramatic breakthroughs can be survivable, if they are matched by equally dramatic restraint, equally dramatic coordination, equally dramatic care, and that is why endurance may be the true test. A species might be clever enough to reach a certain level of power, many might, but to remain at that level, without collapsing under the weight of your own capabilities, that may be rarer than any invention. That may be the talent the universe quietly selects for. When we imagine a civilization's timeline, we often draw it like a staircase, each step a new technology, each landing a new era. But perhaps it's more like crossing a river on stones. Each stone is a transition: agriculture, industry, global connectivity, biotechnology, artificial intelligence, energy abundance. The stones are not evenly spaced. Some are slick, some wobble, some are cracked. And what matters is not how boldly you leap, but whether you keep your balance. Because you do not become a star-faring civilization by touching the future once. You become one by surviving it, long enough for the future to become your home. And in that framing, something subtle happens to the great filter. It stops being only a horror story about extinction. It becomes, in a quiet way, a message about time. The fear inside it is real. The idea that countless civilizations may have appeared briefly and then vanished is chilling. It suggests that intelligence is not a guarantee, that complexity is fragile, that the universe may be filled not with empires, but with attempts. And yet, the great filter is not only a frightening idea, there is hope hidden inside the fear. Because if the future is dangerous, then survival isn't just luck. It becomes something you can practice, something you can aim for, something you can design your civilization around. If the cliff exists, then seeing it matters. Foresight becomes a form of propulsion, restraint becomes a technology, patience becomes a shield. The ability to pause, to question your own momentum, to admit uncertainty, becomes a survival trait as important as any engine. In a strange way, awareness itself is a small advantage. Many dangers are invisible until they are too late. A species might race forward, intoxicated by progress, assuming that the next breakthrough will fix the problems created by the previous one. And sometimes it will. But sometimes the problems scale faster than the solutions. Sometimes the cost of a mistake grows with capability, until a single error is no longer local, no longer survivable, no longer something you can learn from. To know that this possibility exists, to take it seriously, is already a kind of adaptation. It means we can treat certain thresholds with reverence instead of impatience. We can watch ourselves the way we watch unstable stars, aware that brilliance and collapse can be close neighbors. We can build institutions that are not only innovative, but cautious. We can decide that some races should not be run at full speed. And this is where the great filter becomes less like a prophecy and more like a mirror. It reflects back a question that is both sobering and empowering. If civilizations vanish before reaching the stars, then what would it take not to vanish? Not to merely survive in the biological sense, but to survive as a coherent, functioning society, to survive as a species capable of long-term commitments, to survive the temptations of short-term gain, to survive the psychological pressures of living with world-altering power. The hope is not that the universe is safe. The hope is that we can become the kind of civilization that treats danger as real, without surrendering to despair. Because despair is also a failure mode. It can make a species reckless, or numb, or cynical. It can make the future feel pointless, and when the future feels pointless, it becomes easy to burn it for fuel. So the great filter at its best is not a sentence, it is a warning label. And warning labels, quietly, are a gift. They exist because something can be handled safely if you respect what it is. Still, there is another layer to this, because even with warning labels, even with foresight, even with knowledge, there is a temptation to believe that intelligence alone will carry us through, that being smart is the same as being safe, but intelligence alone is not enough. A species can be smart enough to invent and still not wise enough to continue. This difference is easy to miss, especially in a culture that celebrates cleverness. We admire the mind that solves puzzles, that builds machines, that bends nature into useful shapes, and those abilities are extraordinary. They are the reason we are even having this conversation across the glow of a screen, late at night, while the planet turns beneath us. But the great filter, if it exists, may be less impressed by cleverness than by character, because intelligence can amplify anything. It can amplify compassion, but it can also amplify greed. It can amplify curiosity, but it can also amplify fear. It can amplify cooperation, but it can also amplify domination. Technology is not a moral force, it is a multiplier. It takes what is already present in a civilization, its myths, its incentives, its fractures, its unresolved conflicts, and it gives those things more reach. So if a society is divided, technology can make division more efficient. If a society is addicted to status and rivalry, technology can make rivalry global. If a society is willing to sacrifice the long term for the short term, technology can make that sacrifice irreversible. Wisdom, then, is not simply knowledge. Wisdom is the ability to live with knowledge without being consumed by it. It is the ability to coordinate at scale, to create rules that restrain power without strangling progress, to build systems that are resilient, not only optimized, to tell the truth to ourselves about what we are and what we are capable of when stressed. Ethics begins to matter not as philosophy, but as engineering. Coordination begins to matter not as politics, but as survival. Resilience begins to matter not as a comforting word, but as a hard requirement. And humility may be one of the most underrated technologies of all, because humility allows learning, it allows course correction, it allows the admission that a model was wrong, that a plan failed, that a risk was underestimated. It allows a civilization to step back from the edge without needing to pretend the edge isn't there. An advanced society in this view is not one that has eliminated conflict or danger. It is one that has learned how to absorb shocks without shattering, one that can face its own flaws without denial, one that can hold immense power in its hands and not squeeze until something breaks. If the great filter is about transitions, then wisdom is what turns transitions into thresholds you can cross, instead of walls you crash into. And this brings us gently, inevitably, to ourselves, because humanity is unfinished. We like to think of ourselves as modern, as advanced, as standing at the summit of a long climb, and in many ways, we are. We have mapped the genome, we have walked on the moon, we have built instruments that can see galaxies so distant their light began traveling before our planet even existed. But we are also young, not in years, but in maturity. We are a species that has only recently gained the ability to affect the entire biosphere, only recently gained the ability to alter the chemistry of the atmosphere, only recently gained the ability to end civilization in an afternoon. only recently gained the ability to create minds that might one day rival or surpass our own. And we did not evolve for this. We evolved for small groups, short horizons, immediate threats. We evolved to respond to what we can see and touch, to prioritize the near over the far, to treat tomorrow as less real than today. Now we live in an era where tomorrow can be engineered or erased. So the future is not a guaranteed ascent. It is a long project, the long project of becoming a stable species, a species that can manage power without self-erasure, a species that can handle abundance without wasting it, a species that can withstand disagreement without turning it into annihilation, a species that can innovate without destabilizing the foundations it depends on. This is not as cinematic as starships. It doesn't look like a rocket launch. It looks like institutions that hold. It looks like cultures that value truth. It looks like education that teaches systems thinking. It looks like incentives that reward long-term stewardship instead of short-term extraction. It looks like the slow, difficult work of aligning what feels good now with what keeps life possible later. And yes, it looks like planetary stewardship. Because before a species becomes interstellar, it must first remain planetary. It must learn to treat its world not as a temporary campsite, but as a home. Not as a resource pile, but as a life support system. Not as something to conquer, but as something to understand and maintain. There is a quiet irony in dreaming of distant worlds while neglecting the one that made us. Not because space is unworthy of our curiosity. It is endlessly worthy. But because leaving Earth is not a substitute for learning how to live. Even if we someday spread outward, even if we build habitats and terraform and travel between stars, the lesson remains the same. A civilization that cannot sustain itself in one place is unlikely to sustain itself everywhere. The stars do not automatically make you wise. They only give you more room to make mistakes. So perhaps the great filter for us is not a single moment. Perhaps it is an era, a long, delicate stretch of history where our tools have outgrown our instincts, and our survival depends on whether we can grow into the power we have already seized. And then, after all these thoughts, after all these quiet speculations, we return, as we always do, to the night sky, because it is there, above the noise of our days, that the question becomes emotional. You can step outside on a clear night and look up, and the universe does not explain itself. It simply is. The stars shine with a calm indifference that can feel like peace, or like judgment, depending on what you bring to them. They inspire wonder. Because the sky is beautiful, and it is also silent. And that silence can be interpreted in many ways. It can be a sign that we are early, a sign that we are rare, a sign that life is difficult, a sign that intelligence is fragile, a sign that advanced civilizations choose to be quiet, a sign that we are simply not listening correctly. But when you hold the great filter in your mind, the silence takes on a particular weight. It becomes the possibility that the universe is not empty of life, but empty of survivors. At somewhere, many times, the lights came on and then went out, and the stars, ancient and patient, kept shining. In that sense, the universe can feel quietly judgmental, not because it has opinions, not because it is watching with intent, but because it reflects consequences without emotion. Physics does not negotiate. Ecology does not forgive. Exponential growth does not pause because a species is proud of its art, or its music, or its dreams. The universe is beautiful, and it is strict. It allows life, it allows complexity, it allows intelligence, but it does not guarantee permanence. So when we look into the night sky without looking away, we are doing something that is both brave and necessary. We are letting wonder and fear coexist. We are allowing ourselves to be inspired by the same stars that remind us how easily a civilization could disappear. And perhaps that is the proper posture for a young species standing at the edge of its own power. Not panic, not denial, but a calm, steady awareness that what we do next matters. Because now we can return, gently, to the original question. Do civilizations vanish before reaching the stars? It is possible. It is possible that the great filter lies behind us, that the hardest steps were the earliest ones, and that the universe is quiet because life itself is rare. That would be a comforting answer in some ways, even if it makes us feel lonely. It would mean we have already passed through the narrowest gate. But it is also possible that the filter is ahead, that the silence is not about how hard it is to begin, but how hard it is to continue. And if that is true, then we may be living inside the answer right now. Not because disaster is inevitable, not because the story must end badly, but because this era, this strange time when we are powerful enough to change the planet, but not yet wise enough to agree on what it should become, may be the very thing the Great Filter is made of, an adolescence on a cosmic scale, a period where the species is brilliant, restless, inventive, and still learning what responsibility feels like. The greatest frontier may not be distance, it may not be propulsion, it may not be the engineering challenge of crossing light years, it may be learning how to last, learning how to hold power without abusing it, learning how to coordinate without coercion, learning how to build a civilization that can survive its own inventions long enough to use them well. Because the first starship, if it ever launches, will not only be a triumph of physics, it will be evidence of something deeper, evidence that a species learned to keep its world intact long enough to build the ship, evidence that it navigated its dangerous transitions without falling into the dark, evidence that it became stable enough to carry life's fragile flame beyond its birthplace. And maybe that is what the silence has been telling us all along, not with words, but with absence, that the universe might be full of potential and yet nearly empty of permanence, that intelligence may be common, but endurance may be rare, and perhaps the most unsettling possibility of all is this: the silence of the universe may not be asking where everyone is, but whether any civilization ever truly learns how to last.